Thank you very much for the kind introduction, and thank you for the wonderful hospitality here at KAIST. It's always good to be here. So I want to start out with a question for you, and that is, we all know that the integral from 0 to 1 of x, let's make it easy, x squared dx is equal to 1/3. And so my question is, what is it 1/3 of? So numbers are adjectives, and this is 1/3. So what is it 1/3 of? Good. It's actually, you're correct. Miriam gets the correct answer. It's 1/3 of the volume of a cube. Exactly. And so let's look at that very quickly. So if we draw a unit cube, like this, and we put along, say, this axis here, we put a square lying along the x-axis of volume of area x squared. So we put a square like that. And then we can just fill the cube up with 3 pyramids. In fact, if you do this in n dimensions, if we start out in the, if we look in the 4-dimensional cube, there are actually good grid lines on the blackboard, but I don't see them very well, so it's taking me a little bit longer than usual to draw this. So there we go. Line missing there, there's a line missing here, and I think that's it. Yeah. Okay, so if we look at a 4-dimensional cube, and let's label the points, so let's label this as 0, 0, 0, 1, 0, 0, 0. We're going to label this one as the first coordinate, this one as the second coordinate, this one as the third coordinate, this one is the fourth coordinate. Then, there's a line missing here. And if we take this cube right here, that cube is the cube where all the fourth coordinates are equal to 1 in that coordinate system. Then we cone that cube off to the origin. We can see that the volume of that, the 4-dimensional volume of that, is actually 1/4, and with a little bit of geometric patience, you can rotate that around and see that it really does fill up 1/4 of the cube. And for those fans of n factorial, you can cut things up even smaller and fill things up with simplices, not equal angular simplices, but right simplices, so you can fill up the n cube with n factorial simplices just by cutting like that. Here's the second puzzle. It's related to what we just did. So if we take 1 cubed plus 2 cubed plus 3 cubed and so forth, the sum of cubes is the square of a triangle. So that's a geometric fact. And how does it work? So the sum of cubes is this cone that I've drawn, right? The square of a triangle is also a geometric figure. I guess I need one more hypercube here in order to show you that. So please be patient. That's close enough. Whoops, that line's wrong. Okay, that's close enough for what we need. So if we take the triangle in the 1-2 plane and we take a copy of it, transfer it over here. I don't have all my lines in yet. Okay, so we have a copy over there. And I need one more copy of that triangle somewhere. It should be right here. So if I take a triangle times a triangle, so the other triangle lies down here like so. And like so, and like so. Okay, so triangle times a triangle. In the coordinate system, I've taken the triangle with x-axis, y-axis, and then I've taken the triangle with z-axis and the w-axis. And then the resulting topological space is a disk, but this is what we see on the boundary here, and it's triangle times triangle. In particular, if you look carefully in this picture, you might envision a prism, and that's how we're going to prove that these two things are equal. We'll cut this cube into two pieces. Cut the cube into two pieces so that they're both prisms. And then, that's the cut that I want. And the reason I know that's the cut that I want is that before I came in, I measured all the distances from the origin and found out which distances are what. I'm going to take that, turn it around, and glue it back together, and I'll get a triangle times a triangle. Okay, so that's the geometric proof that this is true. There are a lot of other proofs. If you want to think about a simplex as an ordered n-tuple of points in the interval, then a cube is an unordered n-tuple of points. And so you can play with orderings and unorderings and rematch them up and show this as well. So this is where the rest of the talk that I'm going to give you started. So I'm going to give you a little bit of personal history. So Abhijit Champanikar and I were playing around with some scissors congruence and observed that we could prove that the integral from 0 to 1 of x to the n dx is equal to 1 over n plus 1 geometrically just by this trick. We wrote the paper up, put it on the archive, submitted it, and found out somebody had done it before us, which is not such a great surprise. And I did some nice little Mathematica animations of rolling hypercubes around so you could see this. And I showed this to Dylan Thurston, who then asked me if I knew a proof of this, and I didn't know a proof of this. And this proof that I've shown you is a proof that Dylan Thurston, Walter Neumann, and Dave Baer worked out over dinner one night. And I liked the proof very much. And then I was talking with Professor Conway, who asked me if I knew of a proof that of Heron's formula from a four-dimensional perspective. And I didn't. And I know Professor Conway is sort of a competitive type person. And I said, well, I want to try to do something that Conway didn't do, which is very, very difficult. Now, is it turning on? I saw something light up. Okay. And but I couldn't quite prove that on my own. I used the help of an undergraduate student named David Mullins, but I'm still not getting. Okay. All right. So let's see. While we're waiting. So this, as you know from calculus, when you're summing the nth powers, you're computing a Riemann sum for to try to compute the integral. And if you explore in, say, combinatorial algebra, you'll find out that in order to compute the sum of the nth powers, the way that you do so is by means of Bernoulli numbers. So there's something that's known as Faulhaber's fabulous formula. Professor Conway told me the story, and this is a wonderful story. Descartes heard of this Dutch mathematician who could sum nth powers and said, well, this is fantastic. I think I'll go and visit him for a week. And Descartes was a man of leisure, so he was able to actually go and visit. And he stayed for about 2 months learning as much as he could about Faulhaber's fabulous formula. And so Faulhaber, who was a contemporary of Descartes, actually invented the Bernoulli numbers. There's a very, very clever way of summing these things, which I'm not going to tell you today, but Professor Conway told me, and I always have to look it up because it's so clever. He said, you'll never forget it. And that was the kiss of death, so every time I need it, I have to go look it up on the internet. But if you look up Faulhaber's fabulous formula, there's a very cool way of writing down what the Bernoulli numbers are. Now, the Bernoulli numbers are what you use to sum these discrete sequences. And sort of the problem that I'd like to give you, which I don't know how to solve, is to try to interpret the Bernoulli numbers geometrically. They must have something to do with the difference between the discrete picture and the continuous picture. There must be some gaps in those hypercubes. Okay, so this is Heron's formula from a four-dimensional perspective. And so we want to review the Pythagorean theorem. We want to understand the distributive law as a scissors congruence. And we want to show you that two scissors congruences are, the product of two scissors congruence is a scissors congruence. And we're going to understand this in the case of right triangles. And study this in parallelograms and then study it for the Pythagorean theorems. We're going to give lots of pictures. So before I do that, I should also tell you what Heron's formula says. So Heron's formula says that the area of a triangle, if we have a right triangle, any triangle, with side lengths A, B, and C, and for me, A will always be less than B, less than C. I'm going to put the right triangle in the coordinate plane so that this side is P and this vertex is QR. Then the area of the triangle is going to be given by the square root of the semiperimeter minus A, semiperimeter minus B, semiperimeter minus C. The semiperimeter is the perimeter divided by 2. Okay? That's the formula. It's been known for 2,000 years. And it can be simplified a little bit. First of all, let's take off the radical. So we have A squared. And let's multiply through by the denominator. That's 2 times 2 times 2 times 2, so that's 16. And then we get A plus B plus C minus A plus B plus C. A minus B plus C. A plus B minus C. Okay? And we want to expand this out. When we expand it out, it has 81 terms. I'll show you the expansion in just a second, but when we collapse everything down, it's going to be 2a squared b squared plus 2a squared c squared plus 2b squared c squared minus a to the fourth minus b to the fourth minus c to the fourth. Now this is what I mean by a four-dimensional proof of this fact. The quantity on the left is a four-dimensional volume. You have 16 triangles times triangles, the picture that I drew a little while ago and didn't draw very elegantly. I'll show you an elegant picture of it in a moment. So we have 16 triangles times triangles, and we have 9 hyperrectangles. And we take 6 of those hyperrectangles and take the area of the other 3 off, and then we can reassemble them as triangle times triangle. Okay? That's what we're going to do. Oops, that's the wrong way. Page forward. All right. So this is the important part of the proof, and this is the part of the proof that I'm going to explain very, very carefully. The picture, the red picture and the blue picture are the proof of the Pythagorean theorem that I like. And if you measure things properly, you'll find out that that is the proof of the Pythagorean theorem. X times y is z, or x squared plus y squared is z squared, and t squared plus u squared is v squared. And this rectangle times rectangle fits together in this picture, and then there aren't nearly enough lines in the picture to demonstrate what all the hypersolids are. So we'll get those in a moment. All right. So if you do nothing else today, you should know this proof of the Pythagorean theorem. This is one of the classical proofs of the Pythagorean theorem, and it is a scissors congruence proof. In other words, we're going to cut the area, which is x squared, plus the area y squared, and we're going to cut it into these various pieces, 5 of them, and reassemble them so that the length of the diagonal here is exactly the sum of x squared plus y squared. Okay? And I'm not trying to be condescending whatsoever. I just think this is just a marvelously beautiful proof. This is something that when you're playing with your children and you're playing blocks, you should come to this proof. And when you come to it, you should explain it to your children. This is the proof of the Pythagorean theorem. Okay, so let's look at the distributive law. Again, this is what we mean by multiplication, at least geometrically. If we have linear quantities, then we multiply them, we get quadratic quantities. If things are measured in meters, then this is measured in meters squared. And so x plus y times z is xz times yz. It's a geometric fact. If we expand out in 2 different steps, we get these 4 pieces. Now, in the subsequent pictures, there are lots and lots of pieces, and so it helps to, instead of considering this rectangle, I'm going to schematize this rectangle as this vertex, and those vertices indicate the areas of the corresponding pieces. So the distributive law is a scissors congruence. And in 3 dimensions, these are the 27 pieces that we have. We're looking at Q plus R plus S times T plus U plus V times X plus Y plus Z. And if we go along this axis here, Q, R, S increases in the first coordinate. If we go along this axis, T, U, V increases in this direction. If we go along this axis, then X, Y, Z increase in that direction. And so you can always keep track of what the piece is by means of just following the axes. Everybody ready? Okay. So, not quite. So, these are the, if you like to play Sudoku, then I encourage you to play Sudoku in a 4-dimensional hypercube. I think that the game's easier that way. But I don't like to play Sudoku, so I haven't really tried. These are the 81 pieces, and the yellow pieces are the terms that remain. And you can go through this rectangle and find everything that cancels, and Dave and I certainly did. And there's lots of symmetry in what cancels, but we won't really see the symmetry until we expand this out. So those are the 9 terms that I had before. Here we go. Right. My convention for my hypercube is that this is the first coordinate. This axis is the second axis, this horizontal axis is the third axis, and this axis is the fourth axis. And so if we go along, say, the first axis, then you see the first coordinate moves from A to B to C. If we go along the second axis, it moves from minus A to B to C. And probably I have the order of these terms a little bit different, but according to some orders, if you go along the third axis, then the third coordinate goes from A to minus B to C and so forth. So all of the terms here are indicated, and the colors are ugly because actually I used color mixing so that I would keep track of which terms were which, and it was all a percentage of CMYK somehow or another. And so all the terms are telling us, the colors are telling us which terms are of the same type. So for example, and this is really probably the best picture in this sequence, because you see, for example, here you see minus c to the fourth up there, you see minus b to the fourth down in this corner, and you see minus a to the fourth in this corner. And over here, this structure inside the hypercube it's a tetrahedron. It's what you get when if you take a hypercube and you pass it through three-dimensional space, vertex first, then the first thing you see is the vertex, and the next thing you see when you get to the next lattice point is a tetrahedron. If you move again, you'll get to an octahedron. If you move again, you'll get to a tetrahedron. So you see these tetrahedral structures here. You see them here and here, 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 and in the two yellows. And all those terms cancel, okay? Now, go in, select the terms that have those colors, remove them, and then see what else you have. This one is messy. I don't really want to discuss it, but all the terms here cancel. The arrows indicate cancellations. And then you're at sort of the last place where you have terms with two pairs of the coordinates are the same. And a lot of those cancel except for 6 of them. And they're somewhere in the picture. So what I've done is on the right-hand side, I've shown you how you can take this quantity and find a scissors congruence down to this quantity. So you can envision that different parts of the hypercube have negative volume. If you don't like negative volume, then move them over to the other side of the equation. That's fine. Okay. Now we're back to triangle times triangle. And there are 4 congruent shapes. By the way, these pictures that I'm showing you are linear projections of the hypercube. So I am cheating because I'm drawing things in the plane, but there are many angles and so forth that I'm keeping track of on a piece of paper independently. And the linear projection that I'm choosing is ideal for your notebook. So you take 3 centimeters, which is 3 notebook lines, and make that a vertical. It's fairly easy on the horizontal to imagine what 3 notebook lines are. And then the diagonals are at 45-degree angles. Their length is 2 upon the square root of 2, so their length is almost 3. And so it looks like a regular octagon. So you stay on the lattice, and then it looks like you've got a regular octagon. So here we have the triangle times triangle that I drew initially. Then I reflect that back here. I've got these 4 other pieces, and these 4 pieces fit inside the hypercube. This is an alternative picture of it in the central projection. Okay, so let me keep that up for a moment. And if I had a right triangle, then I would have accounted for 4 a square terms here. Okay. But I don't necessarily, so if I have a right triangle, I'm almost finished. But I don't necessarily have a right triangle. I have a skew triangle, and then we have to remember how you prove that the area of a triangle is 1/2 the base times the height. What you do is you duplicate the triangle, reflect it, turn it over, and so you have a parallelogram. And let's see. A squared is q squared plus r squared, and b squared is r squared and p minus q squared in that picture. And we can fill, now this part is a little bit cheating. I actually drew this from the same point of view that I did the other ones. And I know it looks exactly the same, but these are intended now to be parallelograms. Right. I can always linearly map a parallelogram to a square, so I could just put it in the previous picture, but I didn't. And so these are our triangle times triangle, filling a parallelogram times parallelogram. Okay? And how do you know that the area of a parallelogram is the base times its height? Well, you cut one corner off and glue it back to the other. So that's a scissors congruence. And so on the left-hand side, I have parallelogram times parallelogram. On the right-hand side, I have rectangle times rectangle. And here I really did cheat. So I dilated my rectangle down to my standard size hypercube instead of making the dimensions look, at least look to me, quite a bit different. All right, so what do we have inside this picture? Is this a laser? Yeah. This picture here is that upper corner of the parallelogram times itself. So that's a triangle times a triangle. This picture here is a trapezoid times a triangle. This picture here is, so that's actually a blue trapezoid times a red triangle. This is a red trapezoid times a blue triangle. And this picture here is a trapezoid times a trapezoid. And if we put those four pieces into the parallelogram times parallelogram, then they'll fill up the parallelogram times parallelogram. We can reassemble them into the rectangle times rectangle, putting this, so it was in the back over here, we're going to put it up in the front over here, push this one. This is a triangle times trapezoid, so it's going to, this triangular face is shared between those two. This parallelogram face is shared between them as well. So those two go together. Then we put this trapezoid times triangle in the back. And then we put this trapezoid times trapezoid over here. And then we fill up the rectangle times rectangle. And everything works out nicely because things are sitting in two-dimensional space, so there's an orthogonal direction between them. Okay, so we want to do the same thing now with the proof of the Pythagorean theorem. So we want to take this geometric figure, which is a decomposition of a square into 5 pieces, decompose this square into 5 pieces. We'll get 25 four-dimensional pieces, r times r prime times d prime, and so forth. And look at what the geometry of each of those is. Okay. So for example, if we decompose the red square, then we have those pieces. The blue square we're going to reassemble as sums of 2 squares like this. And so now we would have, for example, if we look at this piece right here times this triangle, we would have a triangle times square. This piece would be a triangle times square, and so forth. Okay? And this piece here would be a square times a square, very small piece in terms of our overall geometry. Then we reassemble and get to this picture here. And that's what I mean by a scissors congruence times a scissors congruence is a scissors congruence. So you decompose things, cut them up, take the Cartesian product. They fit together. Again, they fit together because of that 90-degree angle between the two planes. Okay? All right. This means something. I got to remember what it means. This is the problem with putting pictures up with no words. How about right. How about over here? A squared is the sum of 2 squares. And c squared itself is a square. B squared is the sum of two squares, and c squared is a square. So I have to account for pieces of this type, and they're going to be triangle is decomposed as a sum of two squares and then times squares, and then I can reassemble these things like that. Don't worry about this picture so much because we're going to break it down into, each piece is going to be broken down into 5 smaller pieces. So in fact, this is the union of 5 pieces, this is the union of 5 pieces, and so forth. Okay. And they all fill in like that. I'm happy with that process, okay. All right. This is what happens on the set of edges on that diagram. And I'm not as happy with that picture as I could be because there are some lines that are overly thick. All right, so here's catalog. Triangle times triangle, this shape here. Triangle times this triangle, this shape here, and so forth. And if I remember correctly, everything is drawn with the same angle attitudes. So this I haven't rotated this triangle whatsoever. The congruence from this triangle to here is just translation, okay? And the congruence for this triangle over here is always a translation. So these are our 25 pieces that we want to reassemble. And we'll do it 5 at a time. So we have, we're multiplying consistently by this blue triangle here and reassembling them until we get into this block here. Similarly, over here, we're reassembling along this red triangle here. And so forth, and then the teeny tiny piece. Okay, so I pointed out to you that we really did have a very small square times square, and that's what's in here, and I think the shading is a little bit weak, but everything is actually shaded in that piece. So when the physicists tell you that the universe is 11-dimensional and a bunch of them are curled up and really small. So when you have small dimensions in some direction, then the piece starts to look, this looks very much like a triangle. It is actually a triangle times a square, but it starts to look like a triangle just because the relative length here is very small. So you have these 5 triangles times squares and then a square times square. Those fit together to be this. And so just to review, we took a decomposition of this rectangle into 2 triangles. We multiply it by the blue triangle, and we get this picture. We have this rectangle times a blue triangle, you get this picture. This square times this triangle, we get this picture. And those fit together to give me a shape like this. And that is a sum of squares times triangle. Do the same thing over here. We have the rectangle, and the square decomposing as a sum of squares times triangles, and so forth. Sum of squares times triangles, and sum of squares times triangles. There should have been 4 of those, and then we get sum of squares times squares as indicated here. Everything fits together until you get a sum of squares times sum of squares. All right. This is what we're looking at here, this expression here. And a squared, b squared, a to the fourth, and b to the fourth are all expressible as a squared is the sum of squares, b squared is the sum of squares. So everything here is the sum of squares times the sum of squares. These are sum of squares times sums of squares. The a squared c squares are easy to deal with. The b squared c squares are easy to deal with. And the c to the fourth is there's nothing to deal with there. And so this is the expression for a squared as a sum of squares. And this is the expression for b squared as a sum of squares. And just so that the notation is consistent, we set b equal p. And so a squared and b squared, a squared times b squared, is the volume of the hyperrectangle with these edge lengths. The other one, for some reason, I've alternated the a's and b's. And then a to the fourth is the volume of the hyperrectangle with these edge lengths, and so forth. And each one of these hyperrectangles, what I showed you before, each one of those hyperrectangles is decomposed into 25 pieces and can be written then as indicated. All right. So a to the fourth is this times this. We expand that out, it winds up being this, b to the fourth winds up being this, and a squared, b squared winds up being this. And all of those equalities are realized as scissors congruences. Okay? So a squared is scissors congruent to q squared plus r squared. C squared is p squared. So these are also realized as scissors congruences. And I don't know how many times a week it takes me before I get this to work out properly. It's embarrassingly, it usually takes me about 3 times in an evening before everything works out. But here we go. So that's why it's written down, so I don't have to do it anymore. Here's a squared, there's b squared, a squared, and c squared, and so forth. And then the expression, when you expand it out, the correct thing to do, I believe, is to group around p squared minus q squared. This equality is a scissors congruence. And it keeps going. You can check my algebra. We wind up with 4 times p squared times r squared. So what happened? (16a squared is 4a squared times 4a squared. 4 of the a squares fit together to form the hyperrectangle. You take 4 of them and you get one hyperrectangle. You take another 4 and you get 4, you get another hyperrectangle. You take another 4, you get another hyperrectangle. So this 4p squared r squared is the volume of the left-hand side. And the other expression was the volume of the right-hand side, and we cut the volume of the right-hand side up. So what we did was we cut the right-hand side up using the Pythagorean theorem and then reassembled things until we got for hyperrectangles of the correct volume. And that's my story, and I'm sticking to it. Thank you.